Hey guys, in this video we'll be solving improper integrals step by step. These are integrals of functions that exhibit a divergence, or in other words, they become infinite. This can occur in two scenarios. The divergence will occur at one of the boundaries of our integration interval. We see that we integrate from 0 to 1 in this case, and at the lower boundary, namely 0, we see that our function exhibits a divergence. It becomes infinite at this point. In the other case, the divergence does not occur at one of the boundaries. We see here that we integrate from -1 to 1, where in both of these points the function is very well behaved, so no infinities, but we see that somewhere in this integration interval our function becomes infinite and thus we have a divergence. And in this video we will see how to take these divergences into account, because if you don't, then you more often than not will get the wrong result, which is obviously something that you would want to avoid. Now, as always, if you have any questions along the way, feel free to ask them in the comments down below. And with that said, let's just get into the first exercise. In the first exercise, we are going to be solving the following integral. The integral from 0 to 1 from the function 1 over x squared dx. Now, if we would not consider these boundaries, then this would be a very straightforward integral. However, these boundaries make it so that we'll have some more work to do, because we see that in this lower boundary, this function shows a divergence, meaning we get 1 divided by 0, and 1 divided by 0 becomes infinity. And this also becomes quite clear when we look at the graphical representation of this function, so its graph. We see that if we integrate from 0 to 1, which is the same as calculating the surface beneath the curve in this interval, then we see that at 0, this function becomes plus infinity, and therefore we need to be careful in a sense. So how do we now solve such an integral? Well, the first step we already did. It's to identify in this function that we have a possible divergence, so where it might become infinity. And we saw very clearly that this will become infinity when this x goes to 0. Well, this is exactly the lower boundary that we have. And therefore, we are going to do the following. We're going to replace this lower boundary, which is causing some trouble, with some parameter t. And the rest we just copy, so we integrate to the upper boundary of simply 1. The function remains 1 over x squared dx. And how we are going to equate these two is now to make it a limiting process where this parameter t goes to 0. Because in the limit, then we will just get this boundary again. However, it's also important here from which side t approaches 0. It's not from this side, since there we're not integrating at all. It will be from the positive side, since this will be inside our integration interval. So t will approach 0 from above. And since we now have a lower boundary that does not cause any problems, we can just calculate this integral and leave this limiting procedure for later. So we have the limit from t going to 0 from above, and this integral becomes the following. We know, of course, that integrating 1 over x squared is simply minus 1 over x. Because if you derive minus 1 over x, you simply get 1 over x squared. And the boundaries in this case will become the lower boundary t and the upper boundary 1. And this is now very straightforwardly calculated. We still copy this limit from t going to 0 from above of the following function. We first fill in the upper boundary, which then simply becomes minus 1. And then we subtract from this the lower boundary filled in this function. Now this will simply become minus 1 over t. And it is at this point when we do the limiting procedure, when t goes to 0 from above. This limiting procedure does not have any bearing on this minus 1 because it doesn't have any t. So we get minus 1 plus, because two minus signs become a plus, the limit of t going to 0 from above of 1 over t. Now we see, of course, that this limit simply becomes infinity. So this one becomes infinity. So the solution of our integral is minus 1 plus infinity, which is of course equal to plus infinity. And we see that indeed the area under this curve becomes infinitely large. Now you might say that that is quite obvious because, well, our function becomes infinite at 0, therefore the area under the curve will also become infinite, but that is not always the case. And to see how this works, we go to the next exercise. In the second exercise, we're looking at the following integral. We integrate from 0 to 1 again, and now the function 1 divided by 2 times the square root of x. And we don't forget our dx. Now again, the first step is to identify whether this function indeed has any divergences. So where does it become infinitely large? We see that because we have an x in the denominator, if x becomes 0, then this function will become infinite. And this also becomes apparent when you plot this function. Again, we integrate from lower boundary 0 all the way up to our upper boundary 1, which corresponds to, again, calculating the area under this curve between 0 and 1. But we see that at 0 our function becomes infinitely large. And again, we already did the first step, which is to identify that this lower boundary right here will cause some trouble, since simply filling it in will give a divergence. So again, we will replace this lower boundary with a parameter t, which we will then use in a limiting procedure. We again are going to, integrate the same function. This remains unchanged, and we write this limiting procedure. So t going to 0, our original lower boundary, and now again we need to look how it approaches to 0, from below or from above. And we see that the integration interval that we're looking at is positive, and therefore we are approaching this 0 from above. So we take this with us. And at this point it becomes all straightforward. We simply copy this limiting procedure, which we will leave for later on. And then we calculate this integral right here, which is now very straightforward, because we know that the integral of 1 over 2 times the square root of x is simply the following. It's of course simply the square root of x. And the boundaries, again, will be t and 1, which gives us the following. This limit of t going to 0 from above of the following function. We fill in the upper boundary in our function, so the square root of 1, or, which obviously simply becomes 1, minus filling in this lower boundary, which becomes the square root of t. Then we apply this limiting procedure, which only has an effect on this minus t squared, because, this 1 doesn't contain any t, and we get the following. We get this 1 minus the limit of t going to 0 from the square root of t, which is simply filling it in the square root of 0. And we see that our result in this case is simply 1. So this integral, even though at one of its boundaries, the lower boundary, the function itself becomes infinitely large, the area under the curve, including this boundary, is not infinite. In fact, it's simply 1. And that might surprise you, because that would mean that we have an infinitely long line, but the area under the curve of this infinitely long line is still a finite number. Namely, it's simply 1. And that is one of the wonders of mathematics. So now that we know how to tackle integrals of functions with a divergence on one of its boundaries, let's look at the following exercise, where the divergence is somewhere in between the boundaries, so inside of the integration interval. We need to solve the integral from -1 to 1, again from the function 1 over x squared dx. Now the first step remains the same, which is to identify whether this function that we want to integrate shows any divergences, so where it becomes infinitely large. Well, obviously, we see again, as in the first exercise, that when x becomes 0, this function will become infinitely large. The difference now, however, is that 0 does not occur at one of the both boundaries of our integration, and therefore you might be tempted to simply treat this as any other integral. So you integrate 1 over x squared, which we already saw becomes minus 1 over x, and the boundaries are now simply -1 and +1. This can now be very easily computed by first filling in the upper boundary in -1 over x, so we get -1 over 1. Then we subtract from this the lower boundary filled in our function. And at this point we need to be careful with minus signs here. So we subtract the following, so -1 divided over filling in -1. And there's a lot of minus signs here. However, this minus sign in denominator cancels this minus sign, and the only one that is remaining is -1. And we see that if we calculate this, we simply get -1 minus 1, which is -2. So did we indeed get the result here? Well, unfortunately, no, this is the wrong result. And this can easily be seen if we just consider the graph again. So if we plot the x-axis and the function axis, the y-axis, then again, this 1 over x squared is this function right here with a divergence in 0. And therefore, if we integrate from -1 to +1, and we look at the area under the curve, well, then obviously this is not -2. So simply using our normal integration techniques gives us the wrong result. So how do we then solve an integral which has a divergence inside of its integration range? Well, we have identified that there will be a divergence at x is equal to 0, but x is equal to 0 is not one of our boundaries. Therefore, what we do to solve this is to split this integral such that 0 will become one of the boundaries. And so we get the integral from -1 to 0, our divergent point, from 1 over x squared dx, plus the second part of our integration from 0, our divergent point, to +1 of the same function, 1 over x squared dx. So what we did here really is to first integrate this part from -1 to 0, which is this integral, and then integrate from 0 all the way to +1, which is this second integral. And by adding these, we get our original integral again. And as an added bonus, we see that our diverging point is now part of the boundaries of these two integrals. And therefore, we have now two cases of the situation that we had in the previous two exercises, where we need to integrate a function in both integrals, which has a divergence in one of the boundaries of the integral. And fortunately, we now know how to solve this. We simply replace this integration boundary with a parameter t of the same function 1 over x squared dx, and we of course take the limiting process from t going to 0. But again, now we need to be careful how it approaches 0. We see that in this integral from -1 to 0, we approach it from below. So in this case, we approach 0 from below. Then we do the same for our second integral, which becomes the integral from t to +1 of this same function, 1 over x squared dx, plus the limiting process, where t goes to 0, but now of course we approach it from the upper side. So we approach it when t is larger than 0. And now we can simply do the same procedure as we did before, simply computing these integrals. So we get the limit of t going to 0 from below of the following integral, the integral from -1 to t of 1 over x squared, which is simply the following. So we get -1 over x filled in the boundaries. In this case, that would be -1 to t, plus something very similar for the second integral, again, the limit from t going to 0 from above this time, of the following. Again, we have -1 over x, now filled in these boundaries, namely t for the lower boundary and +1 for the upper boundary. This means that we get, again, the limit from t going to 0 from below of the following. We fill in t in our -1 over x, and we get -1 over t. Then we subtract from this -1 filled in into -1 over x, which of course simply becomes 1. Then the same we do for the second integral, the limit from t going to 0, but now from above, of the following, filling in the upper boundary in -1 over x, this simply becomes -1. And we subtract from this, filling in t in -1 over x. This of course becomes -1 over t. And again, at this point, we are ready to perform or take these limiting procedures, but they will only apply to these terms which actually have a t inside of them, and we get the following. We get the limit of t going to 0 from below, so a negative number, inside -1 over t becomes -1 over minus a very small number, and therefore this becomes plus infinity. Then we have this -1, which just remains as it is, and we do the same for the second integral, but this time this t is a slightly positive number, so it approaches 0 from above. And if we take into account that these two minus signs cancel each other to become a plus sign, then we see that this 1 over t, where t becomes a very small positive number, simply becomes plus infinity. So again, we do not forget this minus sign right here. So we get plus -1, and then the limit plus infinity. Now this minus 1 and minus 1 don't really count because we see that we simply have plus infinity, which of course becomes plus infinity. So if we go back to our original integral now, then we see that this integral becomes plus infinity and indeed not equal to this minus 2, which we got by doing this very naive integration method. This also means that this area under the curve between minus 1 and 1 is indeed infinity and not minus 2. And this is how you calculate improper integrals. And if you have any questions, feel free to leave a comment down below. If you appreciate the time that goes into making these videos, give them a thumbs up and consider subscribing. And with that, I thank you for watching and I will see you in the next one. Bye.